I'm going to draw a shape for you, and I want you to identify what it is. Okay, here it goes. I'm going to draw this. What do you think this is? Well, if you said this is the number 9, then you're correct. What about this one? Well, you might say, okay, this is pretty easy. That's the number 8, and you'll be right again too. But here's the bigger question. How did your brain sort of perceive this visual information to then tell you that this is the number 9, or this is the number 8, or this is also a 9, and that's also a 9, this is an 8, and that's an 8, and maybe like a block, this is also an 8. So how was your brain able to decide that you see something like this, that's always going to be the number 9? And because your brain is made of millions and millions of neurons, I believe 10 to the 10 different neurons in your brain, they're basically able to fire a signal if that particular neuron, let's say, has been trained to detect the number 9. So when it looks something like this, it says, I now see the number 9. So your brain goes, okay, that's the number 9. So if you think of your computer, if you think of your brain as a computer, how do you think the steps might go about in identifying what this shape means? So let's see, what you could say that, well, if my brain ever sees a loop, a circle like this, and a straight line right next to it, then it's always going to be the number 9. And if I see a circle and then another circle right below it, and they're attached together, then that's always, within the context, is always going to be the number 8. Okay, that's a fairly good, let's say, algorithm for your brain to be able to distinguish that. And whenever your brain sees these two circles, the neurons that have learned that whenever these two circles are together, they should be the number 8, they will fire, they'll signal, or they'll say on, and your brain will realize that that's the number 8. Well, how do you think a regular computer might be able to perceive this information? Because I want to make it this algorithm, whatever we end up with, I want it to be as close to how our brain might think, how to look at this shape and decide what that number is. So you could start by saying that, okay, well, let's follow along with that idea of different shapes, right? So you have these two circles, and if you put one next to the other, then that's the number 9, number 8, and then there is a straight line, and if you combine these together, that's the number 9. And maybe if you have something, a line like this and a line like that, well, if you combine those, you'll get the number 1, and this is also number 1, and that's also the number 1. Okay, well, what we might end up doing is making things a little bit simpler. Instead, we'll say that, let's say this shape is made of really small little segments here, line segments. So I'm gonna sort of zoom into the number 9, and I'll say that it's made of a segment like this, and then a shape like that, and then a shape like this, and a shape like that, and then maybe one line here and a line here. And if you were to, sort of compile it together, you'll get a circle and a line, and based on this orientation, if you put them together, that'll do something like this. And your brain already knows that if I see something like that, a circle and a line up close in this order, then that's always going to be the number 9. Right? Pretty simple. So let's write down the steps of that particular algorithm. So I will say that the first and foremost, you take your input shape, right? Whatever shape you have, you take the input, and then you deconstruct it into small segments. Right, and then you also want to, based on those small segments, you also want to look at larger segments. And then a third step might be looking at the orientation or order of where these segments go. And then finally, you'll be able to, let's say, classify or identify what that shape means. So if you think of your brain working here, it could be that there are some neurons in your brain that are trained to sort of figure out identify these small segments. And so if a neuron sees something like this and it says, oh yeah, I saw that, and then another neuron sees something like this, and then a third neuron saw like something like this, it's been trained to identify these guys, and then a final neuron identifies something like this, and then you'll say, okay, I have these 4 small segments, and then based on this information you could pass that along. So all of these 4 neurons fired, and they could pass that information along that I fired to another neuron in your brain that is able to detect circles. And then if those all 4 fired, then you say, okay, then I have found a circle here. And then you could then forward that information. This neuron will forward its information that I found a circle to maybe the neuron that knows orientation in your brain. And then finally, you'll be able to decide, given the orientation, where the position is and everything, you'll be able to decide if that particular shape is the number 0 or the number 1, right? Given this input, you'll say that's the number 0. So let's sort of look at a structured example here. So this is my naive interpretation of how the brain might sort of take a shape and figure out if it's either of these 3 numbers. And what I've done here is I've sort of separated my 2 little segments out. So this is, I'm going to say this is layer 1, which is just made up of neurons that are able to identify a small segment in my shape. So this neuron here, this little box neuron, it's only going to fire on or off, right? That's what neurons do. They signal on or signal off, and it is connected to these neurons here too in layer 2. And so if in my shape there is a really small straight line, this segment, then I want this neuron to tell the ones it's connected to that it fired on. And if there was let's say if there was a horizontal line, then I want this to fire on and give that information, provide that it fired on to these connected neurons in the second layer. And then based on that, I also want this neuron to sort of signal forward if it detects a circle in my shape. And we now know that if there is a circle in my shape, then it's highly likely that the final shape is not going to be the number 2, or it's not going to be the number 1, it's actually going to be the number 6. So I'm just going to call this my output layer for the time being. And I'm going to also provide you with the input layer here. And so let's do a really quick example. So let's say this is the shape I want you to go through this network. So take this shape as an input, put this into this network, and try to tell me what number it is. And we're going to first deconstruct this, right? That's sort of the idea. And so I'm going to deconstruct it into a small segment like this, a small segment like this, and then this could be perceived as a straight line. So I'm going to do that. A small segment here, small segment here, one here, and then one over there. So I've sort of deconstructed my shape given to me into small segments, and that's going to be my input given out to this layer 1. And so what's going to happen, what I hope happens basically, is that I'm going to take each of these segments and pass them on here. And whenever a neuron that is able to identify that particular shape sees that particular shape or segment, then it's going to fire on. Now, what I really want to happen is that this neuron will fire on because it sees a straight line here. This neuron fires on because it sees it twice. This fires on, this will fire on, that will fire on because it sees that there. And then I don't want this to fire, and I don't want this to fire, and then I don't want this to fire, right? That's sort of the idea here. And what I'm really hoping for is that I know that this neuron is connected to every other neuron, but I really want to focus on this connection. And I really want to focus on this connection here, this connection here maybe, and then this connection, that one, and that one. So we know that whenever these neurons will fire on, because they found those little segments in that shape, they're going to send out their information to all of them. But to detect the number 6, I really want these neurons to know that information is coming in from these little neurons here. So the red lines are more important than the regular white lines here, because what I hope happens is that if a layer 2 is able to detect a circle exists, because these 4 fired yes, then this layer will know that there indeed is a circle here. And whenever this fires, I really want to see this connection here. So this will go on, and I really want to focus on this connection here. And I really want to focus on this connection here. And I want to focus on this connection here. So again, if this neuron fires on, it's going to send that information to all the neurons in the next layer it is connected to. But right now, for the number 6 to be evaluated, I really want the ones in red, the connections in red, to be very prominent here. And that's sort of what your brain is going to do too. If you give it, let's say, the number, let's use the number 2 here. And I'm going to deconstruct it. So I'm going to say there's something like this, there's something like that, there's sort of like a line like this, and then there's a straight line like that. Well, in that case, what's going to happen is that this neuron will not fire, this will fire, this won't fire, this will fire, this won't, this will fire, and then that will fire, right? So this is over here. This is over here, and then you have these lines, the straight lines. Okay, in that case, I really want my network, when it sees the number 2, what I want it to do is that I really want these particular connections to be really, really prominent. This one here, I really want this connection here to be very prominent, and then I want this connection to be prominent, and then ooh, I'm missing another one, but let's just go with this for now. And so once that happens, I really want, going forward in the second layer, so this neuron now knows that this small segment fired on, so there exists a line like this. And then this neuron knows that this guy fired on, which means a small segment like this occurs. And so if those 3 are fired, passing along this information, I really want then to, this will be on too, because, you know, that line exists here. So I really want this to be prominent again. I really want this to be prominent in that case, something like this. So if that is the case, if it is the case that, let's say neuron 2, 3, 4, neuron 4, 5, 6, 7, and 8 fire in the first layer, and then neurons 1, 2, and 4 fire in the second layer, and then I really want to show you, or really want this model to give me the number 2 as the output, right? So based on a different input, or the shape that I give you, I want different neurons to sort of send forward that information. Now again, whenever this neuron fires, it always sends the information to all neurons it's connected to in the second layer, right? But I really want these ones that I've highlighted in different colors to be really, really prominent, more than the other information that's being sent out. So that sort of gives you an idea that you don't just need the input going through. So you don't need just the input. So we don't need to rely on, we don't want to rely on just the inputs. Instead, you want to think of something along the lines of, okay, what if there was something else? What if there was another value that, when multiplied by these connections going out of this neuron, will only make the red one really, really big value and the others very, very small, right? So every connection that's being thrown out is being multiplied by some number. And if the shape is the number 6, then I really want this red one, this connection going from this neuron to that neuron, to be a lot more prominent than the connection between this neuron and that one. And so in that case, we will have something along the lines of, we'll say, okay, also have weights. So a weight might be something that is applied on every little input that's coming into each of these layers for each of these neurons. And then based on that, I could sort of modify how much or how less I want the magnitude of the firing to be, right? So this is a very, I've made it very confusing here. This looks rather bizarre, but this is sort of a very naive little approach to thinking, okay, that is probably how the brain works. It has billions and billions of neurons that are connected to each other. And then if some neurons that were trained since kindergarten to detect a straight line, whenever it sees the number 6, it will say, okay, I'm going to detect that straight line over here, and I'm going to fire that information off to other neurons that sort of come up with, that are connected to other neurons and that are able to combine together and say, okay, well, this is a circle here, that's a straight line, that's a curve here, so combined together, this whole thing makes the number 6. So that's the basic idea, the gist of how I want this model, this network to be. And because we are saying that it is sort of relies on our brain, we're going to call it a neural network. Right? That's the basic idea of a neural network. So think of neural network as a artificial brain model, right? You're trying to replicate how the brain will solve a problem. And we have so far looked at supervised and unsupervised machine learning algorithms, and they all don't really replicate how the brain might look at the information. And we've used statistics, and statistics basically lets us reason under uncertainty. But if we want to replicate human level, artificial intelligence, then it should be noted that the brain should be the inspiration for our methods, right? Because brain is a very interesting computer. It's got 10 to the 10 different neurons, which sort of have this, they basically form the building blocks of how the brain performs computational, right? That's where it all comes from. So for a neural network, we're going to replicate exactly the thing we did here, but instead of using neurons, we're going to use perceptrons, because they are artificial little things that we have created, and we're saying that these are little neurons in our neural networks that are going to, fire yes or no or on or off based on some information. And I've made boxes here, but the way you usually have neural networks designed is sort of like this. You say, everything is connected to everything else in the next layer, and these two combined together, and these two combined together will give you the output, right? So this could be the output, this could be the inputs here, and that could have a layer 1 here and a layer 2. And so all of these little dots here are basically individual perceptrons. So the network that I showed you earlier is actually very complex, where you have so many neurons, let's say, or perceptrons now connected with each other. So what we're going to do for the time being is just focus on one single perceptron. So a neural network that is made of a single perceptron. It does come handy, and we'll look at the applications for it. But for the time being, let's forget that bizarre connection from different perceptrons to other perceptrons. Instead, just focus on a single one. And the way it is made, the way you sort of create a perceptron, it's sort of very similar to how a neuron is. And with a neuron, you have the dendrite, which is going to be an input. So you're sort of passing a stimulus to the neuron here. So this is the neuron, that's the body of the neuron here. And given the stimulus, whatever it is, you want some output. The axon is the output, and that could be firing on, or that could be firing off, right? And so think of it as on could be 0 and off could be 1. So I want what happens is whenever a input or a signal is given to a neuron, it will fire on or off. It will fire either 0 or it will fire 1. So think of a mathematical function that allows us to do that. Think of a function that will either give us a 0 or it'll give us a 1. And that's a step function, right? That's a step function we're very much aware of. So there is a natural step function in here somewhere, and then what it does is whatever signal this neuron will get, it will sort of either fire 0 or 1, or yes or no, or on or off, and then that information could be connected. That output could be the input again. So input here again. This could be an input to another neuron, and that's sort of how the network worked. Now, looking at our artificial neurons, our perceptrons here, what we've done here is that we're using all of these inputs. Here we only had one input to be defined, but we have several inputs here, and each has its own weight. And again, I've talked about what the weight might be doing here. And what you do here is, if this is the input, you will take the dot product of your weights and your inputs, and you're going to pass it through to a step, function again. So this will also fire 0 or 1, and that is going to be your output. So when the developers thought of making a perceptron, they really looked at how the neuron is made and sort of try to replicate that. So perceptron is truly an artificial neuron, and it is being acted upon by inputs as well as their weights here. So a little bit of information about these guys here, and that is that I'll just say that your inputs are going to be XO, X1, all the way to, let's say, some XN. Just going to make it a big X here. And XO, X0, is always 1. So this input is always going to be 1, and it is called the bias. So whenever we're going to be giving inputs to our perceptron, we're always going to have X0 by itself, and it's always going to be the value 1. And then if these are my inputs, then I have my weights here. And they're basically W0, W1, all the way to Wn. And I'm just going to call them W transpose. So the dot product sort of makes sense in this case. And then I will also have an output function, right? That is being used as the step function here. And what I'll do is the output of some inputs is 1 if the summation of all weights and my data and my inputs is greater than 0, and then -1 if this is going to be I equals 0 to n, and then I'll say same thing here if the dot product between my weights and my data points is less than 0. So this is sort of a combination of these two guys here, right? So I'm summing them up, so I'm taking the summation, and then based on a step function, I'm saying that the output would be either 1 or it will be -1 here. So in this scenario, these x values are our data points. So the attributes for your training data that you provide to this model. And what we have to do throughout this this algorithm is to sort of be able to learn these weights here, sort of come up with what the optimal value of these weights is going to be, so that the correct output is computed based on the input. So say if I had a single perceptron here and it's being used with 2 inputs, x1 and x2, well then I really want the output to be, let's say, 5 when x1 is 1 and x2 is 2. So the inputs will never change, right? Your x values will never change, but what you can do, there's always going to be x0 with 1. What you can do is you can update the weights here. You can optimize the value of these weights so that this combination will always give you the number 5. And that's sort of how this neural network will work.